Okay, so let me start the class today. Today we are going to look at two things. First, I will give you a construction of a very famous code known as Readmore Code. Okay, and its construction and certain basic properties. And then I will start a very interesting topic known as Cyclic Code. And it turns out that cyclic codes are really very powerful way of describing codes, and it's very simple way. So let us start with read Muller code first. There is a book also on this code. Okay, so these are denoted by read Muller r comma m, where r is a parameter from r 0 to m, and the parameters are length 2 raised power m, dimension k. I will tell you what is dimension in a minute, and the minimum distance, certain minimum distance. Of course, I'm going to tell you that. Okay, so one way of saying that these are nothing but set of all vectors f, where f is v1, v2, vm is a Boolean function. Boolean function means that the value of the function is either 0 or 1. A polynomial of degree at most r. But this is one definition which one can describe, but I think I'm going to take even a much more simpler definition, which is very easy to understand. I will construct the generator matrix of the Readmore code. So generator matrix consisting of first all one vector. This is V denoted by 1 bar. Next, I will take half of them as 0. So suppose length of this vector is 2 raised power m. Okay. So length is 2 raised power m, and then half of them, that is 2 raised to m minus 1 zeros, and half of them as 1. Okay, so this we call vector v1. Okay, or I think some notation they take it vm actually, so we can do the same notation as well. Vm. Okay. Then half of them again 0, 1, half of them 0, half of them 1. I call it as vector vm minus 1, and so on. And finally, we have got vector 0 1 0 1 0 1 0 1 0 1. So this is your vector v1. Okay, so this is half of the matrix, means first vector is all one vector, then half 0 half 1. Then look at the half 0 means length raised by minus 1, and put again half 0 half 1, and the other all 1 half 1, you again put half 0 half 1, like that you keep on doing until we get v1, where the vectors are 0 1 0 1 0 1. The vector is 0 1 0 1 0 1, right? So this is one portion of the matrix. After that, we actually take product of these. So now there are m vectors here, and if we take any two vectors, okay, and multiply them, okay, so we may take v1 vm and vm minus 1, we may take vm minus 1 and v1, we can take vm minus 1 and v2, and so on. So out of m we choose any two vectors and multiply them, and I can put them in the next rows. So our vectors will be v1 v2 v1 v3 and so on, right? So basically these are m choose 2. You can choose two vectors at a time, and so on. We can continue this way until we finish with 2. Then we can take 3 at a time, v1 v2 v3 and so on, 3 at a time. So there will be m choose 3, because out of m vectors we have to choose 3 and multiply them. Finally we are left with multiplying vectors, say v1 v2 vr, r at a time. Okay, so these are m choose r. So like that, so first vector is all one vector, then half 0 half 1, then half 0 half 1, half 0 half 1, then half 0 half 1, half 0 half 1, half 0 half 1, half 0 half 1, and so on, 0 1 0 1 0 1. These are the vectors. Then we are taking these m vectors and choosing two vectors and multiplying them. So these are m choose 2 vectors we can produce in the generator matrix. Next, m choose 3, we take any vectors and multiply them. Then you take any r vectors, keep on doing this up to r. Okay, so we can say that we can keep on doing this until we have m choose r. This is the generator matrix of Readmore code. Now, one thing, if you look at the parameters, so length is 2 raised power m, which is clear here. Okay, and dimension. Now, by the structure of this matrix, it is clear that all these rows are linearly independent. So dimension k will be nothing but total number of rows in the matrix. So k is 1. That is the first vector, all one vector. Then m choose 1, that is m, plus m choose 2, m choose r. That is the dimension of this matrix. Okay, and it turns out that one can prove that minimum distance of Readmore code RRM is nothing but 2 raised to power m minus r. So in order to prove this, we can use induction. So this matrix actually can be written in a much better manner. So let me give some examples first before discussing further. Okay. So if I say I want to look at Readmore code 1 3, okay, so r is 1, m is 3. So generator matrix will be 2 cube, 1 2 3 4 5 6 7 8, then half 0 half 1 1 2 3 4 1 1 1 1, then 0 0 1 1 0 0 1 1, then finally 0 1 0 1 0 1 0 1. Okay, so this is the Readmore code generator matrix RM13 and length is here 2q, right? So you can see that the distance is actually 2 raised to power 3 minus 1, that is 4, minimum distance. Okay, so we can do some analysis to see actually that is it, or you can directly compute it. This is, RM13. If I want to look at the geometry matrix of RM23, so that means R is 2 and M is equal to 3. We can have the geometry matrix as, again, first 8, length 8 vector 1, 2, 3, 4, 5, 6, 7, 8. Okay, then half 0, half 1, and then you have half 0, half 1, half 0, half 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. Now, so this is your V1, V2, V3. These are 3 vectors, you can see that. And this is your R1 vector, right? We can actually add rest of the vectors as V1, V2, right? So we multiply these two. So how many will be possible now? M is 3, 3 choose 2, right? That is factorial 3 divided by factorial 2. 3 minus 2, that is factorial 1. Okay, so this is 3 into 2 into 1 divided by 2 to 1, so ultimately 3. Okay, 3 ways it is possible. We need to add 3 more rows, so I can multiply v1 and v2. We will get v1 v2 will be 0 0 0 0 0 0 1 1. Okay, then we can multiply v1 v3. So v1 v3 will be 0 0 0 0 0 1 0 1. Okay, then we can have we have what v1 v2 v1 v3. Next we can have v2 v3. This will be 0 0 0 1 0 0 0 1. Okay, this is the geometry matrix for second order Readmore code, okay, of length 8. So this is 2 cube. Okay, so I hope you got the idea how to construct the code. Okay, so now there is one very basic thing that you can observe by looking at this matrix and this matrix, that R13 and R23 are connected to each other by, because this matrix is part of it, right? So we can actually get a general idea which says that geometry matrix of R plus 1, M plus 1 code can be given as geometry matrix of R plus 1 comma M, geometry matrix of R plus 1 comma M, 0 block, geometry matrix of R comma M. This is how we can construct the geometry matrix of higher order from a lower order matrix. Okay, so in other words, there is a result which says that R plus 1, M plus 1 but can be described by U plus V construction. This is known as U plus V construction, such that U is a code word in R Readmore code of R plus 1 comma M, and V is a code word in R comma M. Okay, so this is the geometry matrix. Now using this geometry matrix, we can prove the inductively that the minimum distance of this code is 2 raised to power M minus R. So I leave this as an exercise for you to show that this is proved by induction. We can prove it by induction easily that this is the minimum distance of the code. Okay, so these are the parameters. One last property I would like to mention about Readmore codes is the following: that the dual code of Readmore code is again Readmore code, and it is given by m minus r minus 1 comma m. Okay, so this is also another property about Readmore code. Okay, so this is all about Readmore code, and of course there are some other. So this is the construction basic parameters I talked about, and some very basic properties. Of course, as I told you, there's a whole book on Readmore code by Bhargava, Vijay Kumar Bhargava. So you can look at that book, and you can find more details about it, its decoding procedures, how it is used in daily life, and so on. Okay, so this is a really very interesting code. Next code that we are going to discuss now is cyclic code. Okay. Cyclic codes. It's a very interesting property, very interesting thing about codes. Cyclic codes are very interesting, and they have wider applications. Okay, almost all good codes are cyclic codes. We can show some of the basics like Hamming codes are cyclic code, Golay code is a cyclic code. Okay, and so you will see how how we can show that these codes are cyclic. I mean, many of these good codes are cyclic codes. So what is a cyclic code? Let me give you the definition first. A code C is called cyclic if first condition C is linear code. Okay, and second condition, any cyclic shift of code word is also cyclic. Oh, sorry. Any cyclic shift of code word is also a code word. Okay, so let us take an example. So what does that mean? If C1, C2, Cn belongs to C, this implies that C, or I can call it Cn minus 1 from C0 if we start. This implies that Cn minus 1, C0, C1, Cn minus 2 also belongs to C. If C0, C1, Cn minus 1 belongs to C, its cyclic shift also belongs to C. Okay, so let us take some examples so it will be clear to us. If you look at the first example, 0, 0, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 0. Now you can see that this code is cyclic. Why? Because if I take any code word, say if I take 101 and I shift it, okay, I do the cyclic shift, I will get 110, which is there in C, right? If I take 011 and do the cyclic shift, again you will get 101. If I take 000, take a cyclic shift, it is again in the code. So this is a cyclic code, okay? And so two conditions are very important. That code should be linear code. This is a linear code because this and this can act as a generator matrix. Sometimes you get a third code word. Okay. Now, if you take this is your first example. Now, if you take second example, 0000, 1001, 0110, and 1111, all four. Now, if you look at okay, 1001 and do the cyclic shift, what you will get? 1100. That does not belong to C, right? If C is this, so this is not a cyclic code. Okay, this is not a cyclic code because the cyclic shift of the code word 1001 is not there in C. But we can make certain changes here if we just interchange third and fourth column. Third and fourth column. And so see what we are going to get. We will get equivalent code, which is 0000, 1010, 0101, 1111. This code turns out to be a cyclic code. I have interchanged third and fourth column. So basically, third and fourth column just interchange, third and fourth column just interchange, third and fourth column just interchange in each code word. Okay, so we get this. This is a cyclic code. So if a code is not a cyclic code, we can interchange the columns to make it a cyclic code. This is a possibility. Okay, interchanging third and fourth columns. Okay, next example. We take 11111 subset of f2 raised to power 5. So this is a code. Obviously, it's a subset, but is it a cyclic code? The answer is, so question is it a cyclic code? And answer is no. Why? Because it is not linear. Zero 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 does not belong to C. Okay. Even though if you take this 1111 and take the cyclic shift, it belongs to C, but zero code word is not there. This is not a cyclic code. Okay. Similarly, fourth, we take 0 1 1 2 2 0 1 1 1 2 0 1 and 1 1 2 0 subset of f3 raised to power 4. Is this a cyclic code? No, not a cyclic code, because 0 0 0 0 is not there. Okay, 0 0 0 is not there. Fifth example, we take a code consisting of all zero vector. Is it a cyclic code? The answer is yes. This is cyclic code because this is a linear, and cyclic shift of all zero vector is again all the time it is there. Okay. Another one example we can take, code generated by all one vector is that lambda belongs to fq. Okay, this is also a cyclic code. Okay, seventh example, if you take the whole space fqn, this is also a cyclic code. You see the beauty, so many trivial codes are also cyclic codes. Full space and space consisting of only zero, both are cyclic codes. Okay. So this is the basic definition and couple of examples which I gave it to you. Now the condition that we described about the cyclic code can be converted into what is known as algebraic property in terms of polynomials. So let us see what does that mean. If you take C0, C1, C2, Cn minus 1, and we assign a polynomial here, C0 plus C1x plus C2x square C2x square plus dot 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 Cn minus 1 x is for n minus 1. Okay. What we can do, to each code word, we assign a polynomial like this. So then what will happen? The cyclic shift means, so if I call this polynomial as Cx, suppose I call this polynomial as Cx, x times Cx will be our cyclic shift. X times Cx will be what? It will be C0x plus C1x square plus C2x cube plus dot 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 Cn minus 1 x raised for n. Okay. Now this will become again by matching back to the code word from the polynomial, provided this x raised for n is 1. Okay. So xcx belongs to C if and only if x raised for n is equal to 1. This is a very strong condition which imposes on these polynomials. Okay, so this gives rise to what is known as polynomial ring. We can call it as fqx, that is the polynomial ring. I will give you a definition: f0 plus f1x plus fm x raised for m for every fi in fq. This is known as polynomial ring. So actually I will give you first example before describing the properties of the polynomial ring. Okay, so I'll take the space z2 raised to power 3. Okay, so we know that code vectors are 0 0 0. Okay, 1 0 0 0 1 0 0 0 1 and 1 1 0. Okay, 1 1 0, then 1 0 1 0 1 1 and 1 1 1. Okay, now if I assign the polynomials here, if you assign the polynomials, this will be 0 polynomial, right? 0 polynomial. Okay, then we have 1, then we have x. So this is your 1, this goes to 0, this goes to x. What we are doing actually, if the code word is c0 c1 dot 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 cn minus 1, polynomials are c0 plus c1x plus dot 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 cn minus 1 x is for n minus 1. We are just applying this formula here. Okay, this goes to x squared, this goes to 1 plus x, this goes to 1 plus x squared, this goes to x plus x squared, and this goes to 1 plus x squared. So this collection is denoted by we have a notation here Z2 x modulo x cube minus 1. Okay. And we denote it by another notation known as R3. And this is known as polynomial ring modulo x raised to power 2 minus 1. So basically, Z2x is all polynomials over Z2. Okay. And we reduce everything by the polynomial x cube minus 1, means when x cube is equal to 1, we get only 8 polynomials. Okay. And so this is nothing but polynomial ring. So I can, do all the properties, like I can add two polynomials. If I add x square and 1 plus x, I'm going to get 1 plus x square, the last polynomial, right? We can do addition here. We can do, so what we can do addition here. We can do subtraction here. We can multiply two polynomials. Okay. So very important thing, we cannot divide. So this is not a field. This is not a field. This thing that we need to keep in mind, because polynomials of non-zero degree do not have multiplicative inverse. So this is not a field. Okay. Here. So the main reason is here because we are taking the the division is by x cube minus 1, which we can factor. Okay. X minus 1 is one factor, and then the other factor of degree 2. So basically, what we can say that if we take gf2x, our notation, sometime we use g2x or gf2x, and divide it by a polynomial f of x. Okay. If f of x is reducible, then this set is nothing but polynomial ring. Okay. And if fx is irreducible polynomial, then gf2x modulo f of x is nothing but is a field. As an example, if we take gf2x modulo x square plus x plus 1, this is a irreducible polynomial over gf2. We remember this is nothing but a field, gf4, field with 4 number of elements. This is a field. However, if we take gf2x modulo x square plus 1, okay, this is not a field. It is a ring. Okay. So because x square plus 1 is reducible, and here in this case x square plus x plus 1 is irreducible over gf2. Okay, so this is a basic difference. So that means if we take a polynomial ring and divide it by a fixed polynomial of some degree, if fx is irreducible, the corresponding polynomial ring becomes field. Otherwise, it is simply a polynomial ring. We can add, multiply, divide, subtract, and so on. Okay. So in our example here, so this is our polynomial ring z2x modulo x cube minus 1, because x cube minus 1 can be factored, it's a reducible polynomial. Okay. So this is, we are getting a polynomial ring. Now I'm going to describe some other basic properties. Okay, the first thing, division algorithm for polynomials. Just like integers, we have that for every pair of polynomials ax and bx is not equal to 0 in fqx is our polynomial ring. There exists unique pair of polynomials qx quotient polynomial and rx remainder polynomial such that ax can be written as qx times bx plus rx. Your degree of rx remainder polynomial cannot exceed degree of bx. Okay, this is the basic thing. Let me do a calculation for you in an example here. In this example, so we are looking at f2x, or you can call it as z2x, whatever notation you like, same notations for the same thing. If we take the polynomial x square plus x plus 1 and divide it x cube plus x plus 1, what we are going to get? Okay, we first multiply with x, so it is x cube plus x square plus x. Subtract it, you get x square plus 1. Okay, everything is modulo 2, you need to keep in mind. Then multiply by plus 1, so you get x square plus x plus 1. We are left with x. Okay, this is your reminder. X plus 1 is your quotient, and we have ax and bx polynomial. Okay, so now we are going to define another very interesting property of polynomial known as ideal. Suppose R is a ring. A non-empty subset I called ideal if two conditions are satisfied. First, a plus b and a minus b belongs to I for every a comma b in I. If you take the elements of the ideal, if you take any two arbitrary elements of the set I and you add them and subtract them, you are in I itself. Second, it is closed with respect to the outside multiplication of the ring. So if you take, that means R times A belongs to I for every R in R and A in I. If you take an element in ring R, multiply it with A, I should get, so this multiplication is closed in I. Okay. So now, keeping this in mind, this definition in mind, let us look at again this polynomial ring example, which I showed to you. Yeah, this example, this polynomial ring. If you take this polynomial ring, so I call it as R. R is this. So I try to extract ideal from here. So it turns out that if I take I is equal to 0, 1 plus x, 1 plus x square, and x plus x square. Okay, so I am taking 0, 1 plus x, 1 plus x square, and x plus x square. So these elements forms ideal. Why? Because if we take any two elements, add them, so 1 plus x plus 1 plus x square will give you x plus x square. We are in the set I, right? We subtract them, again we are in the set I. Okay, and if you take an element from R, if I take any element in R, say x square, and multiply it with, so I'm just looking at the condition R times A. R is element x square, and suppose I multiply with 1 plus x. So we are getting x square plus x cube. X cube is 1, so this is x square plus 1. We are again in I. Okay. So taking an element from the ring and multiplying it with the element of the I, we are getting an element of I. So that is, it is close with respect to the multiplication, scalar multiplication. So this is an ideal. So basically I is nothing but, we can call it as, I. So I is equal to 0, 1 plus x, 1 plus x square, and x plus x square is nothing but an ideal of f2x modulo x cube minus 1. It's an ideal in the ring. Okay. I think some other known examples of ideals are, I think if you know, remember, if set of integers is a ring, so you can have an analogy. We know that 2z, set of all even integers, is an ideal in Z. Okay. That's another example of an ideal. So I think that's all for today actually. So I would like to stop here now. So this is a very basic, I gave you a very basic idea about the cyclic code. I showed to you that how an ideal can be formed. Actually, it turns out that any cyclic code, so now you can see that any cyclic code turns out to be ideal in this ring R. Okay, in this is this ring C2x modulo x cube minus 1. So this is really a very basic definition of ideal. Okay. So I think in the next class we are going to look at some more details about this polynomial ring and some other properties of the cyclic code. Okay. That's all for today. Thank you.